Good morning. We're going to be doing NETA test questions for September the 22nd. So I don't really have a good feel for how long this class is going to last, but we have some questions we need to go over. So uh, covering a variety of subjects. So let's get started. Beginning with some questions from NFPA 70E. It says, you are a crew leader. What's the first thing uh, you would do to test a transformer? Okay, so this was out of a NETA exam probably a couple of years ago. But at any rate, the options are de-energize the transformer. B would be isolate by lockout tagout. C would be complete a safe job safety assessment, and D would gather the crew together for a job briefing. Okay, so a couple questions here, a couple different answers. Some people would say, I want everybody to understand it. It's got to be one of these two right here. And isolation by lockout tagout is never a complete secure way of saying that we have things ready to go and safe to work on. So we would have to do something else. Obviously, it had to be de-energized. But the big question is, which one of these two items makes the most sense? And you're the crew leader. Okay, so as a crew leader, you need to do a job safety assessment. You can't gather the crew together for a job briefing until you've done a job safety assessment. So that's the first thing to do. Now, at Premier, we kind of put that job briefing, job safety assessment all together on one page, and it's acceptable for the crew leader to work with somebody else to help develop that job safety assessment, but that has to be done first. Okay, number two. What is the new risk assessment required in NFPA 70E? Should have had a 70 in there. And this was in 2018, the edition that we're still on till the end of this year. So the idea is that we have this hierarchy of risk control methods. We have that, okay? But also they added human error in there as well. So it's a little trick question. We've included the hierarchy of risk control methods, but that's the new risk assessment. But they've also added human error into the mix as well. So we finally identified that we've got people that are doing work out there, and they could be a concern on our job site. Number three, in NFPA 70E 2018, what's been added to the job briefing section? So this is in section 110, and that includes job safety planning. Okay, so in 2018, one of the big changes in NFPA 70E was to actually separate that job briefing and that job safety planning, making sure that we had that job safety planning done first. It's a primary concern, and then go into the job briefing. Question number four. This one refers back to question one. What's the second step in the task? Okay, so once we complete a job safety assessment, and one of the things that's been added in that job safety assessment and in the qualifications for a qualified person is not only be able to identify the risk, identify the risks involved. But the second part of that is not only to identify them, which we've always been pretty good at, but now we have to go through the mitigation process to mitigate that risk. So the answer to this is like, once you've done that job safety assessment, then you have to do the hierarchy of risk control methods. How are you going to deal with those things? And remembering, uh, the number one item on that list is to eliminate the risk. Okay, eliminate the risk. And then we have other options there, which include substitution, engineering controls. Those are the three effective ways of doing that. And then 4, 5, and 6 would be awareness, and then some policies, and then finally your PPE. those are the least effective ways of dealing with the risks. So elimination, substitution, and engineering controls. That's the way to go. Number 5, again, referring to question number 1, what's the third step to get together? Third step. So the third step is gather together the crew for a job safety briefing. So step 1, job assessment. Step 2, mitigation, which is the risk control methods. Step 3 is to gather your crew together for a job briefing. Pretty good process to go through there. Okay, regarding NFPA 70E again, so we have some points here, and I'm going to give you the articles for these answers. It's not easy to show all the pages, but NFPA 70E should be a good review item for you in preparation for the test. This says you have the need to apply red barricade tape to prevent individuals from getting too close to exposed energized voltage 13 kV. At what distance from the hazard would the barricade tape be placed? Okay, and so you have to look in the charts in 130.7, section E, part 2. It talks about barricade tape. It has to be placed no closer than the arc flash boundary. Okay, so we have two choices here. It's either the arc flash boundary, if I can spell, which should be on the label, or the limited approach boundary. So we can't get it any closer than that. So basically, whichever the furthest away from that actual energized 13 kV, that's where the red barricade tape should be. So I've heard people say, I've heard people talk about, it's like, you know what, it just needs to be 6 foot out there. It's like, that's not necessarily the case. 6 foot will cover that limited approach boundary for 13 kV, but it may not cover for the arc flash boundary. So we want to make sure that people are outside that arc flash boundary as well. Number 2, is it acceptable to have an elastic waistband on the top of your cotton underwear in a possible arc flash situation? So good question. Okay, but that's also covered in section 130.7. This is in part G, 7C. So if you want to find it on yourself, there it is. But basically it says it's acceptable to have an incidental amount of elastic. So an incidental amount is acceptable. Number 3, you're taking a voltage reading with your flute voltmeter. The incident energy analysis indicates 9.2 calories per square centimeter. So this is a question that's aimed toward the NETA questions, the NETA test, but also toward our own standard procedures. If you look at this, it says like 9.2, and we have got to get away, and we've been working that way all for the last couple of years, to get away from the old categories, because labels are going to be changing to where it's not categories 1, 2, 3, 4, but it's going to give us the incident energy level of the clothing, or of the clothing requirement. This one says it's 9.2 calories. So we need to understand that our clothing is basically 8 calories. If you don't look at the label, you just take the clothing that you order off of Tyndall, and that's the old category 2. That's going to be good for at least 8 calories. So what should we be wearing as Premier Power employees? Okay, so this incident energy is greater, exceeds our 8-calorie shirt and our 8-calorie pants. Okay, now you might get lucky and look at the shirt collar and see that it's over 8 and might meet this arrangement, but generally speaking, it exceeds our clothing. So therefore, we're going to go straight to our 40 cal arc suit, because our basic concept is below 8 or above 8. If it's below or equal to 8, our work clothes are great. Above 8, it's a 40 cal arc suit unless it exceeds that 40 cals. Okay, so we're going to have that 40 cal arc suit on. We're going to have our rubber gloves. Remember, rubber gloves, leather outers for everything over 50 volts, 50 volts. So we got the rubber gloves on. We got our safety glasses on. We've got hearing protection. And we've got leather footwear. So that should cover us. Now, understand that also if it was under the 8 calories, all this would stay the same, except we wouldn't have the 40 cal suit in. We have our hard hat and our face shield and our balaclava there. A lot of times people forget about the balaclava portion of it. Okay, skipping over a little bit, and let's get into NFPA 70B. This is an article that we don't get into very often. But it's one of the items covered in the NETA specifications for study guides. So we'll talk a little bit about that. And I've tried to hit just a couple, 3 points that are relatively important. So one of the questions is define the following: continuous duty, intermittent duty, periodic duty, and varying duty. Okay. So let's look at continuous duty. Okay. Uh, so basically, it's a constant load for an indefinitely long period of time. And again, I've got to write so you can read, and I need to be able to spell. So basically, constant load, those sorts of things. How about intermittent duty? Okay. It has intervals. Okay. It has intervals uh, of load and no load, or it can have load and rest, or load and no load and rest. Okay. So that would be the definition of intermittent duty. Periodic duty. Periodic duty is still intermittent, but it has a regular recurrence. Okay. So in intermittent, I don't have any idea of when it's going to turn off and turn off. But on periodic duty, I know it turn have full load, no load, those sorts of things, but there's regular intervals. And in varying duty. Okay, varying duty, I really don't know. You got load, no load, and everything in between, and it's variable. So I can't tell. Okay, question number 2. What's the definition of a power transformer? And that's a question that's kind of tricky for us. So the definition of that is greater than 500 kVA. That's considered a power transformer. Distribution is less than 500 kVA. All right. Then item number 3. This is one of the big high points of NFPA 70B, is to develop routine schedule maintenance. What are the 11 items considered for that? And I'll try to write these out in some sort of legible item or form for you. Number 1 is the potential for personal safety. So if there's something that could risk personal safety, that would be the highest level of concern for developing the maintenance program. Number 2, always think about what the manufacturer says, manufacturer safety. Number 3, let's think about the environment. So the environment that you're working in has a huge impact on the safety program you need to develop. If you're in a steel mill or a granary, those are a couple of items that are pretty harsh to the electrical equipment. So that's going to change the periodic maintenance schedule dramatically. Uh, Operating conditions, and I'm talking about load here. So how heavily loaded is that, okay? And you also have to take in not only is the how heavily is it loaded, but when you're thinking about that part, it's like the equipment rating as well. Number 5, expensive equipment repairs. You might want to take that into account, and that's what's listed in NFPA 70B. Uh, is if it's going to if it's going to cost a ton to repair this equipment, maybe I ought to check it out before I have to pay for that repair. Number 6, extensive downtime. If I have a piece of equipment that's not replaceable, it's on a 64-week lead time or something like that, then I need to take care of that piece of equipment because that could be really disastrous to the business. Uh, it could be the lost production and part of it too. That's part of the extensive downtime. Then you need to take into account the equipment condition itself. Number 8, production schedule. I mean, you can't shut everything down just for the whim of it. So you really do need to consider the production schedule, but that's way down pretty close. Then, how about taking it out of service? The ability to take it out of service. Again, that's pretty low, but it needs to be considered. 10 is failure history. What kind of history do we have on this particular piece of equipment or sister pieces of equipment? Those are both taken into account. And finally, inspection history. Maybe the infrared or oil history or something like that. So those would be the 11 items to be taken into consideration when you're developing a routine maintenance schedule per NFPA 70B. All right, let's move on. We got a couple more questions here that we can discuss. This one's on low voltage breakers. Okay, and I have a Siemens 480 volt 2000 amp breaker. It's equipped with a static trip 3 trip unit. Okay, settings are I got a rating plug of 2000 amps. Okay, long time setting is at 50% of that rating. So long time setting set at 1000 amps. Delay is 4 seconds. 4 seconds at the 6 times a rating. Okay, then item C here is the short time setting is set at 4 times the long time setting with a delay of 0.3 seconds. So question is, using the trip curve on the following page, determine the anticipated trip time you would get after applying 6 times long time pickup or 6,000 amps. So I actually even provided the curve here. So this is what you would call a trick question. I don't think they should have things like this necessarily, but it is a trick question that's been on a test in the last 3 years. So if we go back to the statement, long time set at 4 seconds at 6 times pickup. Okay, 6 times pickup. All right, that's cool. 6 times pickup would be 6,000 amps. That's exactly where I'm picking up at. I'm testing it at 6 times pickup. So your first thought is, it's like, okay, it's going to trip in 4 seconds. But I forgot to look at this section down here. Short time set at 4 times pickup. So short time is set at 4,000 amps. And it's set for 0.3 seconds. So I don't even need to look at the curve. I know that this breaker should trip in about 0.3 seconds. Unless I did something to disconnect the short time, I'm hitting that short time limit. If this statement wasn't even here, then I still wouldn't need to look at the curve because at 6 times it's set for 4 seconds. So we can look at the actual curve here and we can see that we got various areas, probably a little difficult for you to read, but right here is the 6 times window. And I believe that's the 4-second delay. So that would be the curve that you would typically look at for looking at long time pickup. But I got to come right down here. Here is my 0.4 second short time pickup. There's the curve right there. So depending on what the setting is there. So I got the curve. It's a pretty deceiving question. Don't even need to look at the curve to determine the outcome. Logic diagrams. Going to do these because they're more and more prevalent on the exam. So we're going to do these and we'll look at another couple of problems after this. But I want to know what the output Y is here. So this is my truth table down here. And so the question is to develop that truth table. So here's my output Y. And I can recognize that this is an OR gate. This is an AND gate. This is an AND gate. This is an AND gate. So I need to look at this. The OR gate here means that any time any one of these three inputs is high, I'll have a high output. So let's look at down here. Let's start at the bottom. That's pretty easy. The only time this guy is high is when A and B are high. Okay? So let's go down here and look when A and B high. A is high, B is high. So they're both high right there. So the output right there is going to be a 1. So that's when this one would be high. A or A and B. A and B are both on. Okay. How about this one? This AND gate is on when B is on, but A is off. Let's go down here and look. B is on, but A is off. Right there it is. That's that second AND. The top AND gate is on when A is on, but B is off, because I went through the inverter there. So A is on and B is off. So the only time it never is really on is when A is off and B is off. So that's the development of that truth table. And you need to be a little more comfortable in developing those truth tables. Medium voltage shielded cables. From two diagrams below, which is the correct CT connection for overcurrent protection on a phase conductor? So I've got a single phase conductor here, and I'm looking at a potential ground fault right here. So there's my shield, and there's my conductor. Well, if I look at this top article here, if I look at the top layout, I've got the conductor going through that CT. I've got fault current coming here, and I've got all that fault current coming back on the shield. And then I've got a voltmeter here. That's not going to detect a fault because it's got the same current going in, the same current going out. That's obviously a situation that you would typically want. Now, here, the next one down, I got the shield is coming back, and it's going back through the CT and into ground, okay? So it's basically negating the current in the shield because it goes both ways through that CT. So this would be the proper connection. That would see extremely high current going to ground, but it wouldn't see it canceled out down here. So that's where we would have. Now, name the advantages and disadvantages of single point grounding of the shield of a medium voltage cable, grounded only at one end, okay? So what would be the advantages of that? Well, number one, since it's only grounded at one end, there's no induced currents, okay? So there's not a path for current to flow in that shield, okay? But a separate ground wire has to be provided. So I have to have a path for fault current and ground current to return back, but it wouldn't be going through the shield. So I'm actually saving that shield from that current. Since there's no shield current, derating the cable ampacity is not a consideration. So I can actually look at the conductor size in the cable itself, and that's good. And the shield is useful Uh, it's useful in reducing noise and those sorts of things. So that's good. The disadvantage of having only a single point ground is the shield current cannot flow. If there's an open circuit voltage at one end and not grounded, that could be an issue. It does not provide protection against inductively induced noise, so that would be a disadvantage. Now, advantages and disadvantages of multi-point grounding, where I would have the shield grounded at both ends. Advantage is, since grounded at both ends, no shield voltage can be present, so it increases safety there. Uh, Provides protection against both capacitive coupled and inductively coupled induced noises. So I have uh, more protection there. Disadvantage: since the shield is connected to ground at both ends, the current induced in the shield now has a closed path. So it has a return path, and that current varies with the load on the main cable. It could reduce with, it could increase cable heating. Uh, Derating of the cable could be required. But here's the huge one. During a phase to ground fault, the fault current will flow through that shield, and the cable can be damaged because of that fault current, when really it did not exceed the conductor capacity, but the shield is not able to carry that kind of current. So I could actually destroy the cable by having it grounded at both ends. Okay, next one is CT and PT connections. So looking at the diagram here, this one was a question on one of the exams that I had. Uh, what type of relay would be in this application, and what's the PT connection called, and explain the operation of this protection scheme, okay? Well, one thing we got to look at is, like, we've got these PTs connected to the line. So here's the line, and I have PTs connected, and they're connected Y on the high side, Y on the source side, and they're connected. Oh, wow, it's connected. It's called a broken delta. I've got a delta connected here, but it's not connected here, so that's called a broken delta. So one thing I have to understand is, like, what would somebody do something like this? And I want to go back with just a little theory and look at my system voltage. I'm rotating this direction. Here's voltage VA, there's voltage VB, and here's voltage VC. So at any given time in my world, VA would be 120 volts, and I'm going to say that's at 0 degrees. And VB, according to my diagram, is 120 volts at 120 degrees. And VC is 120 volts at 240 degrees. Remember, it's rotating counterclockwise, so everything is 120 degrees apart. So I'm going to whiz through a little math here, but you may want to follow up if you want to ask me questions later on about it. That'd be great. But I can represent everything on this vector diagram in the terms of real and imaginary axes. In other words, real is only X and Y, and imaginary is up and down. Real is X, I'm sorry, just on the X axis, and imaginary is my old Y axis. So this voltage VA, that can be represented as, I've got 120 volts on this X axis right here, and I've got 0 volts on this imaginary axis up and down, because it's right here. If I look at VBC, or VB down here, I can see that that actually turns out to be minus 60 volts and a minus 104. So if I were to look at this diagram, I would say that I'd go over 60 and go down 104, and that would be the same point as the end of this arrow. And if I look at voltage C, that would still be minus 60, because I'm going over to the left 60, but I'm going up 104. So the bottom line is if I add up VA plus VB plus VC, here we go, I'm adding it up, 120 minus 60 is 0. 0 plus 104 minus 104 is 0. I get 0 volts. So this broken delta configuration is looking at a situation where if everything is balanced right here, if voltage A plus B plus C it's all balanced, I've added them all together, and in the balanced situation, I have 0 volts there. But now in an unbalanced situation, let's just say I've got a ground fault and one of these voltages goes to 0, then all of a sudden it doesn't add up to 0. So for an unbalanced situation or a phase fault, one of these will go to 0, and all of a sudden I will have a voltage applied here. So basically, the type of relay I want in this situation is a 59. It's an over voltage relay. So for phase to ground fault, that voltage will go to 0. I'll pick up a voltage here. So I want a relay that's going to see that over voltage and give me an alarm or give me a trip situation. Okay. So basically, this scenario just works out to the point where I can actually verify a fault or find a fault because of the unbalanced voltages. Okay, I thought I'd look just one last second here. We got just a few moments to look at some other types of PT connections, okay? I can have another special PT connection that we see quite often. It looks a little confusing sometimes. Let's see if I can draw it here. So this is a system that we'll typically see in a lot of relay protection schemes. Okay. It's a delta or V connection. Okay. Oftentimes V connection. So I've got A, B, and C phase voltage here, and I'm connecting situations here. So I've got A to B right here, and I've got B to C right here. But still, A to C is still a voltage that is a common voltage, whatever's on this line. So I've got all three voltages present there. But I'm using this transformer in a special way. I'm only using 2 PTs. I'm only using 2 transformers, but I'm going to get everything out I want here because here I've got A, and here I've got B, and here I've got C. I've still got all 3 voltages, and I've got a ground here on B phase because this is a completely separate system, okay? There's no electrical connection from one to the other. They actually influence one another, but it's not electrically connected. So I can put a ground on this secondary side anywhere I want to. So I chose to put it right here on B phase. And if I look at the situation, even though this is 0 volts to ground, I've still got 120 volts here. If I got 120 volt PTs, I've still got 120 volts right there. And guess what? I've still got 120 volts right here. So I've still got all my voltages connected one together, but just understanding that B phase to ground is now 0 volts. Works very well. Saves the cost of an additional PT. All right. So that's a good place to stop for today. So hopefully it's been beneficial to you. Uh, I'm going to stop the recording here.